stop 냠냠 난 그저 밥이라도 먹고 싶어.
I chose Dasmariñas Cavite as my transmitter while Pateros Metro Manila as my receiver. The distance or path length from Dasmariñas Cavite to Pateros Metro Manila is 29 kilometers. Since my path length is 29 kilometers, which ranges between 15 kilometers to 30 kilometers, the frequency I will be using is 13 GHz. Then I'll have 13 GHz and 13.1 GHz as the frequencies for Dasmariñas and Pateros respectively. Shown to you in the screen are all the information needed in a site survey, such as its coordinates, elevation, terrain, weather condition, telecommunications used, and its nearest access roads. Before answering all these questions, first things first, we must need to know the elevations between the transmitter and receiver. Shown in the screen is its elevation in meter per path length in kilometer. In path profiling, it means computation. In getting the earth bulge, there is a formula used. The earth bulge is equal to distance 1 times distance 2 over 12.75 times the K factor. But since we're using 4/3 as K factor for dry rocks, we'll be using the formula earth bulge is equal to distance 1 times distance 2 over 17 instead. After knowing what formula we'll be using, we need to jot down all the given values such as the distances. We need to know the distances from the maximum elevation, which is 154 meters as shown earlier. We'll have 1 and 28 meters for distance 1 and distance 2 respectively. Just substitute the values to the formula to get the earth bulge. Then we'll get 1.647. For the total obstruction, we'll be using the formula additional obstruction plus elevation plus earth bulge. Since there is no additional obstruction for dry rocks, it'll be elevation plus earth bulge. We'll have 155.647 for the total obstruction. The formula 17.3 times the square root of distance 1 times distance 2 over frequency times the total distance, we can get the first Fresnel zone. We'll have 13.05 GHz as our frequency and 29 kilometers for the total distance. After substituting all the given values, our first Fresnel zone is 4.706. In getting the tower heights, we'll be using this formula. First Fresnel zone is equal to height 1 minus total obstruction plus distance 1 over the total distance times height 2 minus height 1. We'll consider the 60% as the minimum path clearance. So we'll just multiply the first Fresnel zone to 0.6 and it'll give us 2.824. The given values for height 1 and height 2 are 142 meters and 24 meters respectively. We'll now compute for the tower heights. Tower height is equal to 20.54 meters. To get the actual path clearance, the formula is actual path clearance is equal to height 1 minus total obstruction plus distance 1 over the total distance times height 2 minus height 1. We'll assume here that our tower height is 25 meters. And we'll get 7.284. To verify its ratio, 7.284 over 0.706 is equal to 1.548. It is verified to be greater than 1. Line of sight, the formula is path clearance plus total obstructions. 7.284 plus 155.647 is equal to 162.931. C first is equal to line of sight minus first Fresnel zone minus total obstruction. 162.931 minus 4.706 minus 155.647 is equal to 2.578. This is the table containing all the computation from 0 meter to 29 meters with all the formulas used earlier. This is the graph from Dasmariñas, Cavite to Pateros, Metro Manila with its elevation, earth bulge, and total obstruction. This graph shows the line of sight and all the Fresnel zones between the two sites. There are two parameters in link budget. These are the losses and gain. The total losses, we have the free space loss or path attenuation, transmission line loss, atmospheric absorption loss, fade margin, and other losses. For the total gain, we have the total loss, transmitter power, and sensitivity. First of all, we still need data from path profiling like the distance between towers, the computed antenna height, the frequency, and the elevation of the two sites. We'll also have an assumed value of reliability which is equal to 99.999%. We'll also have the proposed values which may be based on equipment specifications. These are the transmitter power, sensitivity, and transmission line loss. After jotting down all the data needed, we can now proceed in computing for the parameters in link budget. We'll now start with the first parameter. We'll compute for losses. In getting the free space loss, we need the formula 92.4 plus 20 log multiplied by frequency in gigahertz plus 20 log multiplied by the distance in kilometers. As we get the values from earlier, we can just simply substitute it in this equation. After putting all the values, we'll get 143.96 decibels. In getting the transmission line loss, we'll use the formula, the summation of both antenna heights and wavelength guide multiplied by its TLL multiplier. We'll have 25 meters for our height 1 and height 2. Our wavelength guide will be 50 meters and our transmission line loss multiplier is 0.0229. Our transmission line loss will be 2.29. To get the atmospheric absorption loss, the formula is 7.17 times 10 raised to negative 3 plus 6.09 over frequency squared plus 0.227 plus 4.81 over the difference of frequency minus 118 squared multiplied by frequency squared times 10 raised to negative 3. For the atmospheric absorption loss, we'll have 0.0074. In getting the fade margin, we'll use negative 70 plus 30 log times distance in kilometers plus 10 log times 6AB frequency in gigahertz minus 10 log times 1 minus reliability for the values of A and B. A's for roughness factor while B is for the factor to convert a worst month probability to an annual probability. I'll be having 1 for my value of A since it is a place fall for the category for average terrain with some roughness. And my B value is 0.25 for normal, interior temperate, or subarctic area. Just substitute the given values to the equation and we'll be having fade margin is equal to 36.789 decibels. Moving forward, we'll now proceed to link budget's second parameter, which is gain. First to compute is the parabolic antenna gain. We'll use the formula 17.8 plus 20 log times frequency in gigahertz plus 20 log times diameter in meters. We'll be using 3 meters as the diameter. Compute for the gain by substituting the values and we'll get 49.655 decibels. After getting the gain, we'll now proceed in getting the received signal level and system gain. First to compute is the received signal level. We'll use the formula transmitter output power minus transmitter total insertion losses plus transmit antenna gains minus free space loss plus receive antenna gains minus receiver total insertion losses. We'll get negative 33.67 decibels. Now, it's time to compute for the system gain. We'll get this by using the formula system gain is equal to transmitter output power minus the receiver minimum RF input. The threshold will derive from the equation received signal level is equal to fade margin plus threshold. We'll now have negative 70.459. We can now get the system gain, which is equal to 81.459. Shown to you is the table summarizes all the losses, gain, and reliability for link budget.